All right, let's get started. So today's webinar is on press fit strategies for monitoring. My name is John Lytle, and I'm an application engineer with Promess. Been with Promess for about 20 years. Got a lot of knowledge on applications. And today I have Scott Spencer with us.
Yep, I've been here at Promess for a little over 9 years in the applications department.
So kind of a brief summary of what we're going to talk about is I've broken these down into 5 press fit strategies. And those 5 basically consist of press to a position, press to an external probe, press to a force, press to a rate of change, and press to a relative value. And that's basically utilizing what we call a touch point. We're going to go through those today in some detail, talk about some applications related to them. But first off, I think Scott's going to talk about a little bit about the press that a lot of these apply to.
Yeah, so what we have in front of us here is one of our 3 kilonewton presses. This is an actual press that we sell. It's not a cardboard cutout dummy. This is capable of producing 672 pounds. It has a position feedback and force feedback. The position comes from the encoder on the servo motor. The force feedback comes from a strain gauge located here at the top of the press, which then receives the force and distance feedback for your press fit assemblies.
So basically, all that gets fed back into a control system. In our case, it's either our Motion Pro or Ultra Pro controller, and then we control that up or down linearly. And that load cell then gets compressed, and we get the force feedback, and that's how we program and control based off those 2 sensors Scott talked about. We'll go into a little more detail as far as using external sensors like the external probe as part of the press fit strategy. But let's get started with the first one. The first one we wanted to talk about is press to a position. So pressing to a position is really a really simple way to press fit something together. It's really pretty self-explanatory. It presses to a position. So based off the position feedback that Scott just talked about on the servo motor, we can control to a position. So utilizing our interface and that type of thing, we would program it to move a certain amount, and it's going to move that certain amount. It's going to be a velocity type move, meaning I'm going to put in a speed and acceleration for it. It's going to know where it needs to go, know where it needs to slow down and stop at, and that we utilize that to basically press things together. Around all of these strategies that we're talking about, these motion, these press fit strategies, is going to be some level of monitoring. Since there's a built-in load cell and our position feedback, we can create force over position graphs. We can pull values off those graphs. We can also use what we call gauging steps and things like that to put limits and parameters around that. We'll get into a little detail about that as we go through these different strategies. But back to the press to position, basically I'm going to tell it to go to 200 millimeters, for example. It's going to move 200 millimeters, and then it's going to stop. So whatever's in its way, it's going to press that together. I'll wrap some type of monitoring strategy around that. Maybe I want to know what force at that final position it was at, put some limits around that, and then I can accept and reject the part. So press to position is, although very simple, it does have some drawbacks. Basically, since I'm going to an absolute position based off its home position, an absolute position in space, I don't necessarily take into account any stack up or deflection or things like that. So if you have precise parts, and stack up and deflection don't matter, then maybe press to position is one of the strategies you'd want to utilize. The real advantage of it, like I said, is it's really simple to do. Basically, you're telling it to go to a position at a certain speed. It's going to do that repeatably every time I cycle the press. Yeah. What's an example on that?
So a very good example is a well-known diesel engine manufacturer has a engine block, and inside the engine block there is a set of cam bearings, essentially. The cam bearings need to be put within a specific position inside that block. The block is obviously machined to a high tolerance, and they know where to put these bushings at every cycle. So what they do is they send across a specific position for each one of these cam bushings, and the Promess picks those bushings up and then assembles those in a specific position. If they need to adjust that on the fly, they can by changing the values in the PLC so they get a good part every time.
Yeah, so the PLC is communicating with the Promess controller, and then through variables, we basically can send the value over. The other advantage of pressing to a position is also you generally do it in higher rates of speed. Since it's a kind of a pre-programmed position and the press already knows where it's going, you can go at a higher rate. You can go at fast speeds, full speed in some cases. Kind of an offshoot of the press to position, but if you need more accuracy, there's levels of error or deflection, or you need to press to maybe a part print or something like that. Then a lot of times what we'll do, and this is our second press fit strategy, is press to an external position transducer. And pressing to an external position transducer consists generally, in our case, of a digital probe or an analog probe. So either one can be used. And the advantage of that is it gives you a much higher accuracy in a lot of cases. The digital probe has accuracies down into like the single micron level, or even under that in some cases. And the other advantage that it gives you is you can then mount this external probe anywhere in the assembly. It can be on the end of the RAM if you needed it to be. It can be buried down into the fixturing. And this basically allows you to take any of the error out of it, part stack up, any deflection, errors and other things can be compensated for by positioning this to measure directly on the part that you're pressing to. So that gives you the advantage of the high accuracy, takes the error out, and you can position that to a very, very accurate position. And in our software, we're basically able to, we have a command called press to a signal.
Yes.
And the probe can be part of that closed loop feedback to position to. I think you have an example on that as well.
Yep. So there is a major manufacturer of cooling systems that I've worked with, that they have a fan shroud and a fan blade that they need to set at a very specific clearance. Otherwise, things are going to rub and they're going to have premature failures. So what we did is they have a master part that they are able to set in the system or into this assembly machine. They bring the Promess press down with the probe mounted to the press ram itself and some tooling. We come down, we apply a light load. At that point, we zero the probe, so it is now reading 0 millimeters. Then they return the press, they place an actual part into the system, and what we're able to do is run the press down with a positioning move until it reaches a certain zone. Then we change to the move to signal step. The move to signal step brings the probe down to 0 millimeters. Then at that point, they have a perfect part with the correct clearances.
Yeah, so that gives you that super high accuracy that you need in cases like that. And it's a pretty common thing. We do this quite a bit. We do this with bushing pressing, anything that really requires a gap to be set, maybe a dimensional part tolerance you're trying to hold based off a part print or things like that. So that's our second press fit strategy, which is press to an external probe or an external positioning device. So the third press fit strategy is press to a force. And I would say this probably accounts for 75 to 80% of all the press fit assembly applications that we do, whether it's automotive, aerospace, medical, life sciences, all these different areas we get involved with that require some level of press fit. Press to force is probably the most common, and it's actually I think it's simple. But basically, since we have the built-in load cell, and that load cell is fed back into our controller, we're able to control to a force. So using that same move to signal we talked about, we select our force as our transducer, and then we can control the force. So I put in a target value of, let's say, in this case, we put in maybe 2 kilonewtons, and the press is going to move down until it reaches 2 kilonewtons. It's going to call that its stop point, and then it's going to return back. And then we'll put that monitoring around all that to maybe figure out at that force it stopped at what our position was at, maybe how much force it took leading up to get to that force, and things like that. And then we can put parameters and limits around all that. Another nice thing about the press to force is that built into the step is the ability to slow down as you target that force you're trying to get to. And that allows for much less overshoot. So you're not trying to stop as you get right at the force. As we get closer to the force, we have a compensation factor in there that basically allows us to slow down as we get closer to the target. So that allows us to precisely position to that force. And we get into the levels of a couple of newtons to be able to target that force too. So you have an example on that too. So move the force, press the force.
Yes. So not only can the Promess press push, it can also pull the full rated capacity of the system. We have a well-known tractor manufacturer that we've worked with on several occasions that has an exhaust manifold. The exhaust manifold is placed on a table assembly, and there is the first component of that. There is a shoulder on this part that is joining into the second part. There is a seal inserted inside of here, and the Promess press is actually mounted underneath the table here. As you can tell, my art skills are fabulous. And what we're doing is we're actually pulling this exhaust manifold together instead of pushing, which allows you a smaller footprint of a machine. So basically, as this press is pulling this assembly in place, we're monitoring our insertion force, and we're also looking for our shoulder here.
So generally with the move to force, you're going to always utilize that when you're shouldering, or when the tooling has a shoulder on it, and you're looking for that steep ramp up in force at that point. So in your case, you're able to monitor the seal
Yes.
as it's getting pressed in. And then when that manifold reaches, it must be the head, right?
Yes.
You're able to see that bottom out point, and then you can put that strategy around that and detect that it's made its position and the seal didn't get torn or ripped or anything like that.
Yeah, or it wasn't inserted backwards or something like that.
Right. So that third press fit strategy is press to a force. And I'll reiterate, that's pretty common. We use that quite a bit. Anything from bearing pressing to, like your example, to all kinds of different applications you can think of. And our fourth press fit strategy we're going to talk about is kind of another offshoot of press to a force, but we incorporate position into that, and we call that press to a rate of change. A little more of a complex step kind of on the Promess side. From the user interface, it's relatively easy. But what press to a rate of change is we take the force and position values and bring those into the system as we're moving on the fly and calculate a rate of change based off that. So it's a basic slope calculation. And as we get close to rate changes, we're able to recognize that, as he's illustrating here. We'll kind of illustrate that on the graph, and then stop or do something additional once we recognize that rate change. And this is generally used for scenarios where press to force, you don't want to just put a set force on it, because maybe the part has some sensitivity to it, where if you put too much force on it, it's potentially going to damage it. So you can't just use a straight press to force because maybe the interference fits vary a lot. So you're really looking for that rate difference, or that knee, we call it. Once we recognize that knee, then we can stop, or then we can put an additional amount on relative to that. So the nice thing about the press to rate of change is it's on the fly move. So as things change during the process, as we're pressing it together, we recognize that. And like I said, we can stop or do what we need to do. Basic slope calculation, we're taking in force and position, calculating that, giving you a rate of change number. That number is compared to a limit. Once we reach that limit, we stop. Yep. And what's some examples of that?
So we have quite a few, actually.
I'd say this, actually, sorry to interrupt.
Yeah.
I'd say this is probably becoming one of our more popular strategies that we use. You know, even it's getting close to the press to force, actually.
Yeah. So essentially, what we're doing is we're going in and we're eliminating any part stack up. If you have any fragile parts, pin compliant pressing, things of that nature. But probably the most common one that we've been doing recently is a roll pin insertion into a transmission. There is a park pin that has to stick up a specific height inside of the part so the park lever can engage on this. And with a roll pin, you have very loose tolerances of, how long it can be, how,
well, the diameter
the
of
diameter,
it, because that affects a lot of times the interference fit. And
right.
The real problem with that was they were getting a lot of failures in the field, which isn't good in a transmission, that that pin would fall out.
Yeah,
and
so
you're not in park.
So then your vehicle rolls down your driveway, and then you have some big problems with your neighbors. So basically what we're doing is we're coming in, and the press tooling is pressing on the part until there is a specific hard stop here that the tooling actually sets the height of this pin. And what we're doing is we're measuring the insertion force to make sure it's high enough to where it won't back out or fall out. And then we're actually stopping before we reach a large spike in force, simply that way we don't deform any of the metal inside the transmission or break anything at that point.
Yeah, because there's, I think, a rotating bracket in there.
Yes.
So it's pretty sensitive to that. So the variations in the thickness of the roll pin cause huge differences relative to what we're pressing in, huge differences in the amount of force it takes to press it in. So if you use just the press to force to do that, sometimes it would get pressed too far. Sometimes it would get pressed not far enough, hence it falling out or causing other issues. So what seemed to work out pretty good is that the tooling manufacturer made a step in the tool to be able to set the depth of that. Well, that basically gives you the spike you need. And we were able to recognize that rate change, basically, or that knee where that happened at, using the press to rate of change. And that pushed that park pin in almost exactly the same every time, and then also verified that the force was met and all that other criteria, which essentially gave them the confidence to basically press that together accurately every time.
Yep.
So yeah, that was a big deal on that particular application. The fifth and final press fit strategy we're going to talk about is, we're calling it press to a relative value, but really what it is we're pressing to a touch point. And then basically from that touch point, we're moving a relative amount, a relative force, or a relative distance once we recognize where that part's at. So what this does is it takes our press to force command, or press to signal, we were calling it. And basically, as we utilize that command, once we get close to the top of the part, we slow down and we use a really light force to detect where that part's at. And that's what we call our touch point. Once we recognize that touch point, we can capture the position at that value or the force at that value, and then basically move a relative amount from there. And that can be a distance relative if you're trying to set a height for something, or it can be a relative force if from that point you need to press less force once you've already hit the part, or something like that. So we call that press to a relative value. And I think you also have an application that you worked on specifically related to that, don't you?
Yes. So one of the applications that I specifically worked on was actually a riveting application. The riveting application is basically, the rivets are not really a consistent height, but they know that they need to be deformed a specific amount once it has been touched. So what we actually did is we programmed the Promess unit to come down to touch the head of the rivet. Once it found that, they knew that they needed to deform it a specific distance. So basically you set your squash height. So what it does is the Promess comes in and looks for a specific distance, or excuse me, a specific force. Once that specific force is reached, we go a set distance and we monitor the force on that to make sure that it has been deformed properly.
Yeah, because on a lot of different, on rivets especially, that the height of that rivet varies a lot. They're not a precision made part. So it's imperative that you find where that's at, and then you're able to crush it to a relative amount from there and get that height that's needed. And those are in seat rails, and I can think of a lot of different apps we worked in the past about that. So those are basically the 5 press fit strategies we wanted to talk about today. We'll just kind of reiterate and go over them again quickly here. So the first one we talked about was press to a position, which was really basic. Basically just uses the feedback from the servo motor, the position feedback from the servo motor to press to a position. Pretty rudimentary for a servo press, but gives you the simplest solution. Allows you to go at a higher rate of speed generally, but sometimes lacks some of the control or that you can take out of the process if your parts have variation and stack up. The second one we talked about was an offshoot of that, which was the press to an external position device. And that gives you the higher level of accuracy down to the micron level at that point, and can take your variation out of your process, whether that's stack up in the parts, allowing you to make less precise parts, or if there's variation in fixturing or deflection in the machine and things like that. Allows you to measure directly on the part, and it can also give you the actual part dimension you're trying to press to, which is valuable in some cases, and it'll give you the value that you see right on your part print. So that's pressed to an external position device, and we use generally digital probes or analog probes. We supply those. The third, and probably the most common at this point, is pressed to a force, and that's where we're using the internal load cell of the press as our control loop. So basically we come down and move to a force, and that probably accounts for 70-80% of all the applications we work on. We do a lot of powertrain stuff. We're pressing bearings and bushings and things like that in. We do a lot of medical applications where we're pressing light loads and things like that, and that works for that quite well. Our fourth strategy, press fit strategy we talked about, was press to a rate of change, which then inserts the position factor into that. We calculate slope, recognize rate changes visually on our graph, and then do what we need to do based off that. And that gives you that level of control to be able to not overpress or put too much force on the part, fixturing, or tooling, and that type of thing. And then our fifth and final strategy we talked about, which was press to a relative value. That gives you the sensitivity to find the part and then do something additional to that, whether that's press to a relative position or press to a relative force or something like that. And I'd say my experience, we've done all of these and a lot of applications for them, and they've been really successful. And part of that success is from what we call our PDC, and maybe you can expand a little bit about that.
So the Process Development Center is located here at our Brighton headquarters. We have various size presses set up in a workstation configuration, or we can have them set up however large your parts are essentially. What that's going to allow us to do is we're going to actually give you real assembly data from your process. So regardless if you're prototyping, you have an existing component that you're trying to figure out, why am I having consecutive failures in the field? All of these systems are set up here. We can give you your force and position feedback. We can give you the monitoring strategies, gauging strategies, just based off the information that you have. A lot of times you may actually be overpressing your parts. We get a lot of customers calling and say, hey, I need a 20-ton press. Well, that's because they have a 20-ton hydraulic unit and they only need 10. So
it goes into a lot of like not understanding PSI of a hydraulic system versus how we actually measure real force in pounds or newtons or whatever, that type of thing. So I think we did a webinar on the PDC already, perhaps, and that's called our proven process. I'd recommend you watch that, and that gives you a proven process of how we kind of come up with all this stuff and that type of thing. So that kind of concludes the press fit strategy portion of this webinar. I think now we're going to go into the Q&A. So what do we have?
All right. First one we have is, how accurate are the force and position measurements?
So that's a really common question. That's a good question. We get asked that all the time. Being application engineers, a lot of times we're dealing with the customer up front on a lot of early projects and things like that, and that always comes up. So the accuracies on a standard press system are going to be, from a force standpoint, utilizing the integrated force sensor in the press, you're going to be better than 1% of its full range. And typically you're going to be around 0.5% of that. So whether that's newtons or pounds, you're going to be about, between 1% and 0.5% of its full range. Positional accuracy is a little bit different. You're going to take the feedback from the servo motor, like we talked about, as our standard way to control and measure position. But basically there you're going to be plus or minus 25 microns. And that's under a constant load and constant temperature. For higher accuracies, like we talked about, that was our second press fit strategy, which was pressed to an external probe. Utilizing a probe and closing the loop on that, bringing that back into the control, you're going to be down to the 1 micron level as far as positional accuracy. And that all depends on how it's incorporated and on how other things are designed. But at that point, when you incorporate the probe, you're really turning your press fit station into a gauge. And that's kind of a cool thing, because those two generally in the past never went together. But with this type of technology, you're able to control to that. Next question. Do you have proof that your solution works?
So we have over 100 years of combined assembly experience here at Promess between all of us applications engineers, as well as our mechanical team and our software developers. So again, we mentioned the PDC, or Process Development Center. If you have any questions about your processes, you can actually send parts in, you can bring parts in, and that is a free service that we offer. There's no obligation to you to purchase a Promess system or, spread the word about us.
It basically goes back to that proven process, and that answers that question exactly, because that is how you prove it. Once we get your parts in, we give you that data. You can take that data back, analyze it, do what you need to do, bring it back to whoever you need to bring it back to, and that proves that it works. And you're also partway there of developing the program and seeing how well it works.
Yeah.
Go ahead.
Can you do both at once, press and force location at the same time?
Well, essentially that would be press to a rate of change, because you're kind of incorporating both. But from a control standpoint, you're either controlling to one or the other. But what you can do, or what a lot of times we do, is if we press to a position, then we're generally looking to see what the force is at that position. And then we put limits around the force. If you're pressing to a force, then you generally figure out where it found what position it found that force at, and then you can put limits around that particular position. And then there's a whole myriad of ways you can analyze that. But usually from a control standpoint, when you're getting to the end of the target of where you want to be at, whether that's using the force or position, it's going to be one or the other. Unless you're using a rate of change, then it's a combination of both, where we're calculating force and position and coming up with a rate value based off that. Now, leading up to that final stopping point, of course, you can do either or. So you could have a pre-position that just moves to a position, like I talked about, press to a position. You could use that to engage the part way, and then from there you could hand control over to the force sensor and then target that force. So there is overlap between everything we're talking about. This is not totally black and white. In fact, that we combine some of these different strategies we're talking about to come up with other solutions for specific applications and things like that. But in generalities, these are kind of how we broke it down. But to answer your question, yes and no. Pressing to a rate of change does use both of them. Pressing to a position is only position. Pressing to a force is only using force, that type of thing. Can you press and hold a force for a longer period of time?
Yes. So basically, with the EMAP system and all of our products, we have a mechanical design factor of 2 times. So this 3 kilonewton press is really capable of, let's just say, 5 kilonewtons as an example. So the mechanics itself is a very rigidly built, tested, tried and proven system. And then from the electronic standpoint, they do not run in their peak current situation. They're running in the continuous current range. That way, we're not overheating electronics, we're not wearing out motors and things like that. The other nice thing about our system is we use a very low ratio or no gearbox at all. so you don't have to worry about backlashes and things of that nature, wearing things out, wearing components out.
Right. Go ahead.
What program would you use for installing snap rings, and how can you verify that it is fully seated?
Okay, so as we do snap ring applications actually. So a lot of times that's generally part of the tooling strategy too. Well, how I've typically done them is what I will do is have a positioning move. That positioning move will press that snap ring on, and I'm going to take an example. We're just going to say we have a shaft that we're pressing a snap ring onto a machined out groove in that shaft. Let's say that's kind of probably the easiest to visualize and maybe the easiest for Scott to draw here. But basically, I'm going to have a position move that's going to get the snap ring onto the shaft. Once I get close to where I'm going to reach that groove to where the snap ring is installed at, I'm going to switch over to a press to a rate of change and look for a rate drop. So instead of seeing the knee of force go up, I want to look for it to go down. Once I see that rate change drop, I'm going to recognize that point, and then I'm going to shift control over to the force sensor. And then I'm going to push until I see the force increase up again. Then I know I'm in that groove, and I've reached the other side of that shoulder of that machined out area. So it's going to consist of 3 motion steps in a general sense. It's going to be a position move that looks for a rate drop. And then once I find that rate drop, I'm going to look for a move where I see a spike in force, and then I'm going to stop on that spike in force. And that's how I'm going to basically tackle that. And then I'm going to visually look at that by setting up a force over position graph. And you're going to see that. You're going to basically see where you've now have some level of press fit onto the shaft. You're going to see where the force drops, where you get into the groove, and then you're going to see it spike back up again. And essentially, that's going to be the process I would do, and I would program for that.
Yeah, there's quite a few different ways to do it. One of the common ways is, especially with your tooling, there's usually a couple of fingers that are actually touching and compressing the snap ring into a funnel, essentially. So basically, we run a positioning move, and then at that point, we run a move to signal. And once that snap ring is snapped into that groove, we push a little bit harder on that. We record that position number, and then we know that, okay, as long as it's within that position tolerance, it's an acceptable part. So there's multiple different ways to do it.
Can you explain how to create a program for press to slope strategy? So that would basically be pressing to a rate of change like we talked about. But to create that program, how we do it, we have, depending on what controller we're using, we have a couple different ways we do it. We have what we call a live variable or a live expression. And what that allows us to do is take in our sensor inputs, which are force and position, and read those live as we have a velocity command moving the press down. Then we wrap around those steps, we wrap around some conditional statements that basically say, when I reach X position, start calculating my rate of change. And then we have some other conditions that say, when I've reached the rate of change, or I reached the final position, or I reached too much of a force, I have an abort routine. So basically, I put these conditions around that to develop my press to slope strategy. But essentially, the slope calculation is going to be a standard slope calculation. It's taken force and position, or it's taken position where it's at from the previous position, the force where it's at from its previous force, doing the deltas on those, and then dividing that to come up with a rate of change value. And then that rate of change value is compared to a set value that we want it to recognize, and then do whatever we need it to do after that point. But you're still going to have, in most of these strategies, you're going to have some type of pre-move that rapids down close to the part. Once we get close to that part, we'll start pressing it in. Well, there'll be a trigger point where we're going to start calculating the rate of change. Once we recognize that rate of change, we're going to stop on that rate of change and do something additional, or just stop there and return back. But we'll put parameters around that say, hey, if I get too much force and I don't see the rate of change, I'm going to abort. If I see not enough position or too much position, I'm going to have conditions around that to stop and abort as well. So those are kind of how you do that in a nutshell. And that also gives you some safety in there so that you're not pressing too far or not pressing far enough. So hopefully that answers that. If you want any more detail on any of this stuff, just call Promess at 1-800, not 1-800, 810 229-9334. And we can talk with an application engineer, and we can talk in more detail on some of that type of stuff. We can also do all that in our PDC. Why don't we take one more question? 2 more, maybe? I'm looking at, we got quite a few questions here. Which one would you say is the best for linear insertion into a cylinder block?
I think that says liner insertion.
Oh, liner insertion. I'm sorry. Liner insertion into a cylinder block.
So it is generally a move to signal step. Essentially, we've done actually quite a few of these applications with quite a few major engine manufacturers, from agriculture to automotive to heavy industrial vehicles. Basically, you have your cylinder liner. There's a set of seals on there. There's usually a packing at the top. As we're inserting, we're looking for those particular seals for the water jacket. We're looking to make sure that the proper packing's in there, and if there's any shim height. Usually that's done in conjunction with some sort of external position transducer. So what we're going to do is we're going to come down, we're going to apply a specific load to the part. After that, we're going to relax a little bit, usually back off to a known force. Then at that point, some probe readings are taken to check your deck height or your head height. And as long as that's within an acceptable range, it's a pass. If not, we can apply an additional force to finish seating that liner all the way in.
So basically, you're verifying that everything is in there and packed correctly, like Scott said. And then we take in, we generally use about 3 digital probes for that.
Usually 3 or 4.
And that tells us if one side's sitting higher than the other. We can kind of check perpendicularity based off that. So that's generally how we do a liner for a cylinder head or something like that.
Let's see, what type of controller does this use? Can it be integrated with a vision system?
So generally, our systems come complete. So we supply our controller, and this is a controller Promess manufactures. And we have a couple different ones. One's called our Motion Pro controller. The others are Ultra Pro controller. And those controllers generally interface with a PLC or some other device on the station. So it could interface with a vision system as well. We have different ways we communicate, one being just discrete I/O, so standard 24-volt DC inputs and outputs, or it could be through a field bus. So it could be Profinet or Ethernet IP or things like that. So generally can interface a couple different ways, and that's across the board for our controllers that we use. So to answer your question, yes. Can you manually move it and have the cylinder remember the manual move to repeat the move?
So in the long and short is yes. Inside of our programming steps for position moves and move to signal, there is a button in there that is called manual motion. So basically at that point, you're able to set your component, whatever that may be, under the press. You can jog that down to a specific height. Then at that point, you're just going to need to copy that number into the step. And then from there, you would be able to repeatedly run that program. So it's a little, an extra step maybe, besides just jogging and saying, okay, go here. But that is a good idea. Let's see. What recommendations do you have for pressing in bearings to prevent damage to the bearing?
So I would recommend, if it's a sensitive bearing and you don't want to overpress it, generally bearings get pressed into a pocket that shoulders on the bottom of that pocket. Mm-hmm. So there's 2 ways to do it. If it's not ultra sensitive that you don't damage the bearing with a high amount of force, then I would just use a press to force. Be real simple. A lot of times simpler is better in a lot of these types of press fit strategies, but basically I would just move down and press to a force. I would maybe use a position move to press it in part way and control over to the force sensor, and and look for a force and then stop at that force. If it is sensitive and you don't want to put too much force on it, then we move to the press to rate of change. And basically we would find that knee of where it shoulders in the pocket and then stop at that point. One more question, and that would be, which strategy would you say it's best for seat and guide press in a cylinder head? Basically, I'll answer that because I've done a lot of work on cylinder heads and different types of strategies for that. But for the guide, so we use two different strategies for the guide and the seats. And generally we have two presses opposing each other, and we kind of use them in conjunction with each other. So a lot of times we'll press the seat in first, and the seat's real simple. You just use a press to a force. And that seat basically gets pressed to the pocket in the cylinder head. And we press until we reach some force, and then the press holds at that point. And this is where it's important to have a press that's capable of holding force for a long period of time. And then on the other side of the cylinder head, or underneath, or however that cylinder head's oriented in the machine fixture, we press the guide in. And the guides generally get pressed to a dimension or to a position. But a lot of times with those guides, since it's a steel guide going into an aluminum housing, it creates what we call stick slip. So there's a lot of noise in the press fit part that causes issues. So it can get pressed too far or not far enough. So something we really haven't talked about here, and another strategy we have built into some of our commands, is what we call a compensation move. So when the press is holding that seat in and the head, we press the guide in from the other side at a high rate of speed. So we use a press to a position, but around that position we have a compensation factor. So as we get to higher forces, it automatically puts more position into that position move to compensate for the big variation in forces we get from the stick slip we were talking about. So it's called press to with force compensation we use for the guide. So we use kind of a modified version of a press to position for the guide, and then we just use a press to force for the seat. So that's generally how we do the valve seat and guides. And we do a lot of that. We do that with all the major automotive manufacturers, agriculture, things like that. Yeah. So they're telling me I got to wrap this up. We could talk for hours about applications. And if you have more questions and things you want to talk about experience we've had with applications, don't call the 1-800 number because that was wrong. Call Promess at 810-229-9334. And thanks for joining us. Our next webinar is September 15th, and it's called Closing the Skill Gap with Smart Assembly Systems. And again, thanks for joining us.
Yep, thank you.